So we're continuing with the June 2015 M2 paper from Edexcel. Here's question 4. It's the ladder's question. Right, so let's just draw the situation. We've got a ladder against a wall. So let's draw the ladder. There's the wall and the floor. Let's get the ladder in there. Okay, so let's draw it here. Okay, so we're told that it's a rough floor and a rough wall. So we've got reaction force here, and I think it's said that the friction's limiting, and it's mu against the ground, so it's mu r. Let's call the reaction force here S. Sometimes people get a bit mixed up with the direction of the friction, but it's definitely upwards. Imagine what would happen if it slipped. If it slipped, you would expect the ladder to go this way, it kind of start rotating almost, wouldn't it? And the ladder would go this way, and friction always goes to opposed motion, so that is definitely the direction. And we've got this is 1/3 of S because we're told that friction is limited. The weight is W and it's a uniform rod. We're also told the angle. And the question is find the coefficient of friction mu. With these questions, I tend to like to come up with 3 equations, and normally 1 moment's equation and 2 resolving equations, particularly when a ladder's involved, because the resolving is normally easy because there's no angles or distances. So I think resolving's easy. Let's do the moments equations first though, and we'll take moments about the doesn't actually say which is the top. The other end, B, is against a rough vertical wall. So yeah, B is the wall. A. So let's take moments about B. Right, now it probably I'm gonna draw on the components here just to make it abundantly clear. The component of the weight there, that's W cos theta. Then we've got a component of the friction which is perpendicular, which is mu r sine theta, because it's away from the angle. The marked angle's there, so it's mu r sine theta. And then this angle here, r, that's theta here, so that's r cos theta. So those are our resolved angles perpendicular to the ladder, and we know that this is A and that's also A. So that should enable us easy enough to take our moments equation. We've got R is the only one that's going in this direction, anti-clockwise. R times 2A cos theta is the moment of the reaction force at A. Now that's equal to the 2 anti-clockwise forces, the weight, which is W cos theta times A, plus mu r sine theta times 2A. Now, I haven't worked with the angle theta. I know that theta is easy to find, but I tend to like to write my first equation with the angle theta marked in, and then deal with it from there. I think if we divide through by cos theta, we'll get tan theta, and it'll avoid converting everyone to cos and sine. So if we divide by tan theta, I'm also going to do a bit of cancelling. We've got the A cancelling as well. So yeah, we've got A cancelling here, here and here. So let's divide through by cos theta, and we're going to get 2r equals to W plus 2 mu r tan theta, but that's, we know tan theta is 5/3. Right, I'm not going to do anything with that yet, because let's see what happens with our resolving equations first. Okay, so let's resolve, because as I say, I like to resolve the mark scheme. For those of you who've got hold of the mark scheme for this, I actually suggest two resolving equations, and it does work, obviously fine. Especially with lattice questions, so I tend to just two moments equations, I should say. I tend to think of resolving because resolving vertically and horizontally so easily seems like a wasteful almost not to do this. So let's resolve vertically. It's a third S plus R equals W. That is really, don't get much easier than that. No angles to consider and no distances, which is why, as I say, I like to use these. Resolving horizontally, we just get S equals mu R. So we need to combine these three bits somehow. Okay. As I say, normally three equations with with statics questions is what will get us there. And as I say, I tend to take one moments equation and two resolving equations, well, it depends on the question, obviously, but that's the pattern we tend to like to go for. So, right, okay, so let's just substitute, because this one doesn't involve S at all. So let's substitute for S into here, sub for S. We get 1/3 times by mu R plus R equals W. Okay. Now I'm almost got these two combined into one equation, so I want to combine this with this to work out mu. Now, it goes against my natural inclination, but I'm going to substitute for W. I'm going to substitute for W, which goes against my natural inclination, because often our answers are left in terms of W. But otherwise I'm going to substitute for R and get an expression for R from here and R from here and equate, and it's only going to end up in the same place and a load of work to do. So although I wouldn't normally substitute for W, because often W is in our final answer, here I notice if I put W in there and substitute it for in there, I was going to cancel from everything. I'm just going to be left with an expression with mu in it, and that's all we need to find. So let's just do that. Substitute for W. So that's 2R equals 1/3 of mu R plus R, that's W, plus 10 mu R over 3. So now we can see that R is going to cancel. Okay, so hopefully that's going to get us our value for mu. So we've got 2 is equal to 1/3 of mu plus 1 plus 10/3 of mu. So that gives me 11/3 mu is equal to 1. So that gives me mu is equal to 3/11. Okay, so and that's it. 9 marks. Okay, it's come out quite nicely. Okay, let's have a look at the next question, which it will be question 5, I think. Okay, question 5 is work energy question, or at least part B is. Well, part A is really, because it tells us about the work done against friction is 245 joules. So if I just redraw this diagram here, we've got a reaction force here. We've got, because it's moving, friction must be limiting, and we've got a weight of 10g because the mass is 10 kilograms. And the angle alpha here, which we know, because tan alpha is 5/12. So if I resolve perpendicularly, I will get R, the familiar one we see when we resolve perpendicularly. R is 10g cos alpha. Now, if we do our little playing around with our triangle, we have 5, 12, 13. So cos alpha is 12/13. So R is equal to 120g/13. Okay, then the next part, so that's R, so that gives us mu F is equal to mu R. So that means that F is equal to 120g/13 mu. Okay, so we've got the frictional force in terms of mu. Now we know the work done against friction is 245, and this is 6.5 newtons. So we can therefore say, because work is equal to force times distance, we've got 245 is equal to the force, which is 120g/13 mu, times by the distance, which is 6.5. Okay, now you'll forgive me for just doing a bit of cancelling here rather than going straight to my calculator. We've got 245 is equal to 120/2, because that's 6.5/2. 6.5/13 cancels with 2, times 9.8 times mu. So we've got mu is equal to 245 divided by 9.8, and that's also divided by 1/60. Just working out, 245 divided by 9.8 is equal to 25 times 25/60, or 5/12. Right, now, if this were me, I could easily lose a mark here, because the mark scheme actually says they will not accept a fraction because of the use of g as 9.8. Obviously, g is not exactly 9.8. We use the rubric 9.8. We're not allowed to use 9.81 or anything like that. But we need to recognise it's not exactly 9.8. So the argument is, I think it's pedantic myself, but the argument is, because g is not exactly 9.8, we're not allowed to give an exact fraction here. So we give the answer to either 3 significant figures, or, because of the use of g, probably better off giving 2 significant figures. You'll notice I swap between the two depending on which I feel like at any particular time. Really, if they're going to be like that, I would have said, why are they accepting 3 significant figures when it's rounded to 0.98? When it's rounded to 9.8 anyway, so surely 2 would only be appropriate. So what's wrong with a fraction in that case? But there we go. That's what they do. It says clearly in the scheme, do not accept 5/12. Cannot have an exact value following the use of 9.8. So I could have easily fallen foul of that myself if I hadn't been reading the scheme before I've prepared this video. Anyway, this is part B. Now it says using a work energy principle. It's projected from A. Right, so we've got the point A here to some point B, and the velocity at A is 11.5. Let's draw it up again and time on it. So we've got 11.5. It's gone up 6.5, and we want to find the velocity that it is here. Now, of course, we need this because it's going to involve gravitational potential energy. We know this angle's theta here, so this is 6.5 sine theta, which is equal to 6.5 times by sine theta is going to be 5/13. Okay, so that's basically going to be equal to 5/2, so that's 2.5. Okay, so it's 2.5 is the vertical distance there, which we're going to use in our equation. But the way I tend to like to express the work energy system principle is using this equation. By external force. Can't remember where I saw that or where it was. I think a former teacher once, former colleague once pointed out to me, and I think it's a nice little structure to express the work energy principle, something to go on really. Right, now the only thing we need to be careful of is of signs. So if it's a loss or a gain, now it's going to have lost kinetic energy. So this needs to be negative. So we want the least, V is going to be less than 11.5. It's lost kinetic, so it's final takeaway initial basically. We are told the mass, so it's half times 10 times V squared, which we're trying to work out. Take away the initial, this is the delta KE bit here. Times by the initial velocity, which is that. Now, obviously, we're going to use our initial point, our lowest point is our 0 PE. It will have gained in PE, so positive, and that's going to be the mass times by 9.8 G times by 2.5, the vertical distance up. Now we need to be careful, that's going to be equal, so that's the delta KE bit. The work done by the external force, it's going to be negative because it's work done against friction. Friction takes mechanical potential energy away from mechanical energy, so to say, away from the system. So it's a negative. But we're given it, so we don't have to work out the force. We're given it in part as that number, the actual work that against friction, basically the amount of energy that's mechanical energy is taken away from the system because of friction is that. The negative is because the energy has been taken away. If it were cyclists going up a hill or something with a driving force, then that would add to the system, but here it's taking it away. Right, okay, so that gives us 5V squared is equal to 5 times 11.5 squared, taking it all over to the other side, plus, just multiplying that as much as I can do in my head at the moment. Even when I use a calculator, sometimes I like to do some of the things in my head. Just be careful you don't get it wrong. But I think it's less likely to go wrong if you're just trying to do the simple things in your head before committing to a calculator. So it's 5V squared. This bit taken over, that's 5 times 11.5 squared, and then we've got 10 times 2.5, which is 25, times by 9.8. Wait a minute though, that's take away. and take away 245. Okay, so now I'm going to go to the calculator and work out what all this amount is. So that's 5v squared is equal to 171.25. So we've got to divide that by 5. We get 34.25 and take the square root of that. 5.85 to 3 significant figures. Okay, or 5.9 is the other acceptable answer here. Okay, I think you're getting the message now. Okay, 2 or 3 significant figures always. Don't dare in mechanics. Those of you who do stats, often 4 is okay, but don't dare and give any more than 3 in mechanics papers in general. You may well be penalised if you do. Okay, so let's go on to the next question. Question 6. It's motion in one dimension, variable acceleration, or motion where velocity, displacement, acceleration are a function of time. We've got v equals 2t squared minus 9t plus 4. So it's at rest when v equals 0. So this doesn't get much more straightforward for M2. We're equating that equals to 0, which obviously can factorise 2t minus 1 and t minus 4 equals 0. We've got t equals half and t equals 4. It does say times when it's at instantaneous rest. So basically what's happening is we've got a velocity time graph. It's quadratic and it's doing this, half to 4. Okay, so then for part B is to find its acceleration when t equals 2. Acceleration is equal to dv by dt. So that's equal to 4t minus 9. So when t equals 2, acceleration is equal to 4 times, when t equals 5, should I say? That'd be a shame, wouldn't it, to do something so. Number of times you see this happening, you're just thinking about the next thing, thinking I can do this easily, and then just miss out 20 on giveaway marks. Don't worry, I'm sure I did it all the time. So there we go. Acceleration is 4 times 5 minus 9 is equal to 11 meters per second. Right, now part C is going to be a bit more involved than it might first appear, because we really need to consider the motion between 0 and half and between 4 and half and between 5 and 4. Okay, so we've got, if you try and integrate and just put 5 in, then you're just going to get the wrong answer, because you're going to get the displacement, but it wants distance. And what's happening is the particle is, first of all, going in one direction here. It comes to instantaneous rest after half, and then it starts coming backwards again. Here comes to instantaneous rest again, and then it goes off again. If we put 5 in, we will get just the distance it's gone from the origin to where it is after 5 seconds. So we need to consider all of those. I don't normally use limits in these questions. I normally work out C and all the rest of it, but I don't know. It just seems as though I'm going to just break a habit of a lifetime and work out, because basically it's the area under this graph. It just seems the best way to just put limits in it. For those of you who have taught in the past, you'll know I don't normally use limits in mechanics in differential equations or mechanics questions, but here it just seems to be the way to go. So we're integrating this expression. Now, I don't really want to spend a long time talk about integration because hopefully we all know what we're doing here. And that's between 5 and 4. Okay, and that equals two-thirds times 5 cubed minus 9/2 times 5 squared plus 4 times 5. Take away 2/3 times 4 cubed minus 9/2 times 4 squared plus 4 times 4, and that comes to, just working that out, that comes to 25/6. And then if I integrate now for the 4 to the half bit, I've got 2t squared minus 9t plus 4 dt. That will be equal to 2/3 times 4 cubed minus 9/2 times 4 squared plus 4 times 4. Take away 2/3 times a half cubed minus 9/2 times a half squared plus 4 times a half. Okay, and that equals to, I do confess I'm using the integration function on my fx991es plus to make sure I get an accurate answer. That gives me minus 343.24, but just because it's below the axis, this is basically means, all that means is it's gone back from its start, position point. So when we add them together, we're going to make that positive. And then finally, if we integrate between half and naught of 2 times a half squared minus, let's put the function in again, 2t squared minus 9t plus 4 dt is equal to 2/3 times a half cubed minus 9/2 times a half squared plus 4 times a half, and the naught bit is obviously naught, and that comes to 23/24. So the total distance is all of these three added together, but obviously making that positive. So total distance is equal to 25/6 plus 343/24 plus 23/24, and that equals to 19 5/12. And here, because there was no g in it, it's perfectly okay to leave as a fraction, and in some ways desirable. Okay, not too bad, bit repetitive for the last question. I think we'll do questions 7 and 8 in another video because it's been half an hour already with this one. Okay.